In today's lesson, we'll be taking a look into grade 12 rates of chemical reactions. The rate of a chemical reaction can be simply referred to as the rate at which the reactants are used up or the rate at which the products are formed in a chemical reaction. Based on this, we can therefore define the reaction rate as the rate of change in the concentration of the reactants used or the rate of change in the concentration of the products formed per unit of time. And this can be calculated using the formula change in reactants used divided by time or change in the products formed divided by time. This is once again clearly illustrated here on this rate experiment simulation, one of the three simulations in the reactions and rates PhET simulations. Firstly, we can choose from these various reactant options, simulating a hypothetical reaction between A and BC in different colors meant to represent different types of reactions in terms of energy changes. Here we can select how many atoms of A we want to start with, then how many molecules of BC we want to start with. We can make any one of these become in excess as is typical of many reactions. Then adjust the initial temperature, which affects the total average energy in the system. When I click here to begin the experiment, notice how these A and BC will be getting used up as the reaction occurs. And because this is a reversible reaction, they also will be getting formed. Hence A is decreasing from 12, then going to 10, 8, 9, 6, 4, 6, then 7, and so on and so forth. And for the BC molecule, it started at 20, then went to 19, 18, 17, 14, 16, 12, and so on and so forth. Notice how these amounts of the reactants used correlates and affects the amount of the products formed. And as the amount of the reactants used goes up and down, so does the amount of the products formed. Now once again, the rate of this reaction is equal to the rate at which these reactants are used up or the rate at which these products are being formed. There are 6 factors that affect the rate of chemical reactions, namely the concentration, pressure, temperature, surface area, a catalyst, and the nature of the reactants. We use the collision theory to explain how each one of these factors affects the rate of chemical reactions. According to the collision theory, particles, atoms, molecules, and ions can only react when they collide with each other. However, not all collisions will result in a reaction. Hence, there will be effective collisions and non-effective collisions. Collisions that result in a chemical reaction are called effective collisions. Remember, in a chemical change reaction, the chemical nature and the chemical properties of a substance changes as new substances are being formed. So according to the collision theory, the rate of a chemical reaction is determined by the following factors. Firstly, the number of collisions per unit of time or the frequency of the collisions. Secondly, the energy of the colliding particles. And thirdly, the orientation of the colliding particles. This energy graph shows us the energy changes in this reaction, and you can think of these reactants of this reaction having this energy potential around here, and the products on the other hand having this much higher energy potential around here. This is an example of an endothermic reaction where the energy potential of the products is higher than the energy potential of the reactants, and the enthalpy delta H is positive. This top part of this graph from here to there represents the activation energy. So basically, according to the collision theory, for a chemical reaction to occur, the atoms or molecules have to collide, and then it is only the atoms or molecules that will have the sufficient energy to overcome this activation energy that will react and form products. I will illustrate how the frequency of collisions, the energy of the particles, and the correct orientation affects the rate of chemical reactions. and of course how these three, the frequency, energy, and the orientation of the particles, are affected by the 6 factors previously mentioned: the concentration, pressure, temperature, catalyst, surface area, and the nature of reactants. And of course, how all these therefore affect the rate of chemical reactions. To illustrate the basic principles of the collision theory, I will use the single collision simulation. Here we once again have the reaction A plus BC, which, should the reaction occur, will produce this AB plus C. Now with this simulation, this atom A is now lying on top of this spring, which you can pull and let go to hit this atom A. Note how the green total energy line on this energy graph increases as I pull the spring. Now letting go of the spring will once again hit the atom A, which will then make it collide with this molecule BC, as it is lying straight along its path, as you can see. Now observe how when I release the spring with the total energy line below this activation energy, the reaction does not occur, and there is no change in the identity of these substances. So these are therefore non-effective collisions, which would also be observed if, despite the energy now being clearly higher than the activation energy, but if the orientation of the colliding particles is not correct, then therefore the collision will also be non-effective, and no new substances will be formed. However, if both the energy of the colliding particles is sufficiently more than the activation energy, and if the particles are correctly orientated during the collision, then new substances will be formed, and a chemical reaction will definitely occur. Once again, the frequency of these effective collisions with sufficient energy and the correct orientation determine the rate of chemical reactions. The frequency of the collisions affects the reaction rate. So if we increase the concentration of these reactants, we see that the amount of the products formed rapidly and almost immediately increases. This indicates that the higher the concentration of either one of the two reactants, A or BC, the particles collide more frequently, and the probability of effective collisions increases. This would also be true for gas particles at a higher pressure. At a higher pressure, the gas particles are compressed into an effectively smaller volume, which would increase the concentration of the gas particles per unit of volume. This would once again increase the number of effective collisions, which would in turn increase the rate of the reaction. This will also be true for solids having a higher surface area. At a higher surface area, the solids are literally more exposed to collisions from the other reactants than they would otherwise be at a lower surface area. For example, chunks, lumps, or marbles of a substance has a much lower surface area compared to its powder. With the powder, the solid will have a much greater frequency of collisions, which would of course increase the reaction rate. Now, increasing the temperature of the system effectively increases the average kinetic energy of the particles. The particles move at a higher velocity and hence collide more frequently. This once again increases the number of effective collisions, which in turn increases the reaction rate. So for this reaction, you can see when we increase the temperature, the kinetic energy and velocity of the particles increases, which once again increases the rate of production of these products A, B, and C, hence cause an increase in the rate of this chemical reaction. Now once again, note how increasing the temperature increases the total average energy of the particles, which in turn increases the reaction rate. Since the higher the total energy of the particles, the higher the probability of some of these collisions being effective collisions, since they will be beginning at a much higher energy potential, which would then make their energy potential be closer to overcoming this activation energy and therefore forming products at a much faster rate than before. Lastly, for the effect of a catalyst on the reaction rate, imagine adding a catalyst to this reaction. The effects of a catalyst would be to provide an alternative path at a lower activation energy. Therefore, more particles will suddenly have the sufficient energy to overcome this lowered activation energy. Thus, the number of effective collisions will increase, hence the reaction rate in a catalyzed reaction will also increase.